Hello, everybody, and welcome to today's webinar from NBS, which is covering embodied carbon calculations and in particular how to apply those to BIM objects. The presentation today is not only going to be from NBS, but also from Circular Ecology. And before we proceed, I'd like to just thank our sponsors for the webinar, Johnston's Trade, who've kindly sponsored this session. The speakers for today are going to be myself. I'm Lee Jones, Head of Sustainability at Avexo. Avexo is NBS's parent company. And alongside me will be Dr. Craig Jones, who is the Managing Director of Circular Ecology and founder of the ICE database. Just a little bit of housekeeping before we get stuck in. The webinar should last around 45 to 60 minutes. Attendees' microphones are muted. If you want to ask any questions, please pop them in the chat and then we'll follow up with those independently after the session. So what we're going to cover today, I'm going to give a bit of a background as to why NBS are doing what we're doing. If anybody's not gathered, we're going to be publishing a embodied carbon calculation guide and how to apply those to BIM objects. So I'm going to give you a bit of a background into that, why we feel it's important, why generic data is important, and particularly in terms of carbon values. Then Craig's going to give you an overview of LCA generally and circular ecology. And then we'll pass back to myself and I'll talk through the forthcoming NBS carbon authoring guide, give you a walkthrough of that, and then discuss next steps in terms of when it'll be released, how you can access it and all that kind of thing. If anybody's not familiar with who NBS are, NBS is the National Building Specification. We're the UK's #1 specification solution. We provide our leading software, NBS Chorus, to the specification community. So whether that's architects, designers, contractors, consultants, engineers, local councils, anybody that's involved in the specification writing process pretty much would rely on NBS for that solution. And then in tandem with that, we provide NBS Source for the manufacturing community, which allows them to list their products, materials, systems in the NBS ecosystem and connect those to the specification, making it a seamless integration for specifiers to actually select and spec manufacturer products. So to begin, I thought it would be best start with EPDs. Now, EPDs are environmental product declarations. For anybody that's looking at obtaining carbon data for products, materials, systems, in terms of understanding what impact their selection is going to be having on their project, EPDs are by #1 the sort of first port of call that most people will think to look at. They are standardized to international standards, so they are transparent, and the data within them is standardized to the typical life cycle stages, which Craig's going to cover in his presentation in a short while. They can enable accurate whole life carbon assessments. They provide informed and lower carbon material selection if the product is a lower carbon value. And they also then support things like regulations, sustainability frameworks. So if you're looking for BREEAM, for example, or you've got specific local regional requirements, such as the Greater London Authority Plan, getting these type of carbon values allows you to complete those assessments with accurate data. And I think one thing that tends to go a little bit missed is it drives industry competition. So in a world where we're trying to decarbonize continuously, manufacturers, and certainly the ones that are leading the way with this, are seeing this as a USP in terms of their product marketing. And it then by default means that the competitors of those manufacturers also then start to take aim. NBS Source has a wealth of EPDs in terms of things that we have listed on the NBS Source website. In the background, there's an image there from our sponsor, Johnston's Paint, that have a number of EPDs for their coatings, but they're available for a multitude of different materials, from carpet tiles right through to insulation and everything else in between. When we think about EPDs, some of the data that's contained within them tends to get used a little bit more than others. This slide is from the NBS's 2024 Sustainable Future Survey. Just a little note on that, if anybody has used this data or found this useful before or kindly participated in those surveys, we will be launching the biannual one towards the middle of this year, so keep an eye out for the invitation on that. But we asked people a variety of different questions around sustainability as a theme in terms of construction. And when we were looking at the usefulness of EPD data, the embodied carbon typically sits right at the top. So A1 to A3, which is the material production stage. So that's digging raw materials up out of the ground through to transporting to the factory and the manufacturer making them. So that cradle to gate piece is coming up as the most important. Reason being, outside of the in-use stage, which coincidentally comes second from things like energy use, what goes into the building is typically the second, or if not the biggest chunk of the total carbon over the whole life. And then that coincides with the construction stages as well. So we've got that clear ramp there. So this webinar is going to focus very heavily on embodied carbon. We will talk about some of the other stages in a bit of detail, but primarily embodied carbon. Now, whilst EPDs are great, they're not always what is needed, depending on what the timeline is in the project, wherever you are. But sometimes they may not also be available. And that's where generic data comes in. So there's lots of leading bodies, including Circular Ecology with the ICE database, that provide generic carbon data sets. But in a world where governments are looking to achieve net zero, we're seeing this with our European entities. There's already mandates in Europe in terms of having to do an embodied carbon assessment at planning stage, and then even in some cases later down the line as well. The UK government have started to look at this now. Last year they appointed AECOM to do a review. We've got a little snapshot of the front page of their guide there on the screen now. But what they found was that with certain EPDs, there's inconsistencies across carbon data sets. So the user's got to be very, very aware of what is and is not included in the EPD. A great example of that might be two rain screen, glass rain screen cladding system providers. One may have an EPD for their system and it may not include the glass. The next one may have an EPD for their system and it does include the glass. Now, on that basis, the carbon emissions are going to be completely different to some degree. So the user needs to check what is and isn't included in there. There are also things where you can go into how things were measured, what software was used to actually calculate the EPD and such. But overall, what is and isn't included is quite a big thing to note. There are significant gaps in product-specific EPD data. So whilst the industry is on a big ramp up, and no doubt Craig will talk to you about EPDs and how you can create those if you are a manufacturer and want to progress with that. There are product categories that tend to be lower than others in terms of what is available in the industry. And that's where generic data sets come in. So you can actually fill those gaps where EPD data doesn't exist. Now, that said, there are gaps in generic data sets themselves as well. So if we're looking at applying carbon reporting as a mandate in terms of the UK construction sector, there's a bit of a bridge that's got to be covered in terms of getting to that point where the industry's ready for it. And in all, that gives a bit of uncertainty in terms of the carbon assessments as a whole. So generic values then, this is where you would have a carbon value for something like a brick wall, but not necessarily manufacturer specific. So you would have aggregated data that would come from different research, whether it's academic or it might come from a selection of manufacturer EPDs that have then been aggregated and averaged out to give you this value. There are lots of different places where you can get different things from, but the most concise and trusted one in the UK being the ICE database. They support optioneering, particularly in terms of early stage. So if you are in that concept design stage and you're coming up with different iterations of building design and you want to evaluate different costs or different carbon counts or different just design details for your client to give them those choice of options, you may not necessarily know who the manufacturer is going to be at that point. The chances of that being likely are slim. So this is where generic data really, really comes into its own. You can provide those calculations and you can benchmark what that should be at that point. But also, as that project progresses in terms of the technical design stage, it's really useful where EPDs aren't available. So if you are getting to technical design, stage 4, and you know all of the different manufacturer products that you want to specify, if some don't have EPDs available, you can plug those holes with generic data. So it has a place. It's really important, and that's what we're going to be talking to you about today. So on that basis, I'd like to pass you over to Craig from Circular Ecology, and he will talk you through the ICE database and who Circular Ecology are, and how you can access this type of information.
Thanks, Lee. It's a pleasure to be presenting at today's webinar. I'm Dr. Craig Jones. I'm the Managing Director of Circular Ecology, and I work for a company, Circular Ecology. We're an environmental consultancy founded in 2013. We specialize in environmental services, so whole life carbon assessments for construction projects, organizational carbon footprints, life cycle assessments, environmental product declarations, and a range of environmental consulting services. We also host the Inventory of Carbon Energy database, which I'll also discuss today. Now, I like to give a bit of wider background and context. I'm not quite sure about people's backgrounds when they join events like this, but I find it's always useful to go back and have a look at the wider definition of sustainability. So we talk a lot about carbon nowadays. However, the big picture is really sustainable development to achieve sustainability. Now, this is a bit of an old representation of sustainability, known as the 3 pillars of sustainability on a sustainability Venn diagram. Now, this shows the 3 pillars as social, economic, and environmental. Now, what I like about this representation is when you balance 2 of the 3 factors, you end up with different situations that are not quite sustainability. So if you balance social with economic, you end up with an equitable situation. If you balance environmental with social, you end up with bearable. And if you balance economic and environment, you end up with viable. But really, you need to balance all 3 factors to end up with a sustainable situation. Now, carbon gets by far the most attention, but where does carbon fit into this? Well, carbon is a subcomponent of the environmental sphere. There are many other issues in environment, particulate matter, toxicity, water, resource depletion, hazardous waste, etc. So a long list of environmental indicators in the environment sphere. But carbon is by far the most talked about topic that we hear about daily in the news and at events. Why is that? Well, if we go and have a look at CO2 emissions from man-made activities, this here shows the amount of CO2 emissions going back to the 1760s, so a long time ago. And what you can see is this is carbon emissions from man-made activities, so primarily burning of fossil fuels. Now, this here, you can see that you don't need to be an expert to see the unsustainable trend that it's going up, the rate of increase in emissions on the chart here. There's a few things that I find interesting about this chart. First of all, is when you look at when the emissions started to go up, about here, if you can see my cursor on the chart there, it's about the end of the Second World War-ish that the emissions suddenly dropped and then went up at a really unsustainable rate. So for whatever reason, the emissions have been going up, escalating almost like a rocket ship ever since then, over a period of decades. So we have really been talking for quite a few years now about reducing our carbon dioxide emissions. However, you can't really see much evidence of them declining on a worldwide scale here. So we have much more work to do. In fact, since 1980, which is when almost all of our political targets are national, international, to reduce emissions from a 1990 baseline, CO2 emissions have risen over 50%. So we've got much more work to do. Now, carbon footprinting, whole life carbon assessment, carbon life cycle assessment is a decision support tool that can help us manage our emissions better. So that's what we're here to discuss today in the context of buildings. Now, in the context of buildings, a whole life carbon assessment is used to manage the life cycle emissions of a building. Now, looking at this chart here at the top, it considers the emissions going all the way back to the cradle, which is extraction of materials and fuels out of the ground. So from a life cycle perspective of the production of a building, it goes all the way back to digging out ores for metals and everything needed to make building materials, fuels, etc. So there's the activities around extraction raw materials, which starts to be considered for the embodied carbon of what is the carbon footprint to make a building material. Moving around clockwise, we have the transportation of raw materials to manufacturing sites around the world. Then you've got the manufacturing of building materials, transport to site, and then when it gets onto site, we've got construction site activities of the contractor, their fuel consumption, the embodied carbon of construction waste, the waste management emissions of sending that waste to disposal, landfill, incineration, recycling, etc. Then we have operational carbon. Operational carbon consists of two components. One, the operational energy to run the building, and also the in-use embodied carbon. The embodied carbon to replace carpets, windows, cladding, all of the materials over the lifetime of the building, be it 60 years, 100 years, etc. That has an in-use embodied carbon impact too. Then we have the eventual end of life of the building. When the materials and products come to the end of life, they need to go through disposal, recycling, incineration, landfill, etc., or reuse. If they do achieve reuse, they can close the loop here and go back into a new life cycle to become made into new products and materials to fit into a circular economy. Now, the sum of the whole lot's whole life carbon, embodied carbon plus operational carbon. Now, we're going to start to talk about generic embodied carbon data, because if you wish to do embodied carbon calculations for your material, your product, your part of the design of the building, then generic embodied carbon data is a useful data source, particularly before you know the specification of materials, or before you know the brand that you're going to use. Now, in terms of generic data, we do publish a generic database called the ICE database. And by generic, it really, by definition, is shared by, typical of, or relating to whole groups of similar things rather than to any particular thing. So when we look at embodied carbon data, we're not looking at brands, we're not looking at very specific products made in a specific factory by a specific company. We're looking broader, higher level. What's the impact to make a meter cubed of concrete, or a kilogram of rebar, or a meter cubed of softwood timber on a generic basis before you know the actual brand or location you're getting the materials from. Now, that's in contrast to specific data, which would know the brand or material that you're getting the product from. Now, when it comes to types of generic embodied carbon data, there are many different types. So on the top left there, good data sources, industry bodies, trade associations often publish now embodied carbon data or environmental product declarations that represent their sector kind of typical products. Moving around clockwise, we have generic embodied carbon databases like the ICE database, which I'll talk a bit more about today. We also have collective EPDs, environmental product declarations that might represent average data or representative product data, often published by trade associations or industry bodies. Then we have generic LCA databases on the left there. Key databases are EcoInvent and Gabi, which are used for most of the EPDs out there. So there's various data sources for generic embodied carbon data that are really useful if you want to quantify the whole life carbon of your building project. Now, one of the main data sources is called the ICE database, the Inventory of Carbon and Energy database, which I first made when I was a researcher at the University of Bath under the supervision of Professor Geoffrey Hammond. Now, it contains data for about 200 different construction materials, and it's been downloaded by tens of thousands of people from around the world over the years. We don't truly have full stats of how many have fully downloaded it, unique users around the world since it was first released, but it has been tens of thousands, probably over 100,000 or more. It is a free to download database on the Circular Ecology website, so you can download it from there, and you will find generic embodied carbon data for construction materials like aluminium, timber, cement, concrete, steel. Now, since we released ICE version 4, which was one of the recent updates, we introduced a new system to register for permission to use the data for non-educational use. And we had over 1,000 unique organizations around the world register for permission to use the ICE database for commercial use within 90 days of launching of the ICE version 4.0. We had good representation of consultants, academia, architects, manufacturers, and construction companies. So it's still a very well-used database as a generic embodied carbon data source. Now, in the ICE database, if you download it, it's an Excel format. You will find data, embodied carbon per kilogram of materials. So here shows an example for concrete, general concrete, a 20 to 25 megapascal concrete, a 30 megapascal concrete, a 35 megapascal concrete. And you'll find, there's hundreds of different factors for concrete in there, I believe, because concrete's a bit unique in that there's not really standardized set exact recipes that everyone uses. They're all different mixtures provided on a project by project basis. So concrete's probably a little bit more unique from a material perspective in that regards, but there is a lot of data for concrete mixtures in the ICE database. And we do have on our website an embodied carbon calculator for concrete that you can put in your actual mixture from a concrete design certificate and get an estimate of the embodied carbon of that actual mixture of concrete out. But you'll also find more standard data for, let's say, steel rebar, European-made rebar, stainless steel, various data, timber, aluminium of certain types in the ICE database. So lots of useful data, often presented per kilogram or per meter cubed of materials, so you can apply it to your actual building projects. Now, why is generic data important? Well, generic embodied carbon data is used at stages where they have the greatest potential for reduction of emissions. So if we have a look at a representation of the carbon reduction potential by the design stage of the project, so really at the earlier stages of the project on the left, we have the largest carbon reduction potentials because less is known and specified about the project at the earlier concept stages of the project. So really, you want to start the estimates of whole life carbon, embodied carbon of the project as early into the project as you can, because you have the biggest opportunity to reduce emissions. However, even if you're at technical design stage or construction, you can still reduce the carbon of that project, even if you're only starting at that stage too. So there are good carbon reduction opportunities throughout the design and construction process of the projects, but if you can, ideally starting at concept stage is the most ideal starting point to look at measuring and reducing whole life carbon emissions. Now, generic embodied carbon data can be used throughout the design stage of the project. Now, whilst it's most often used at concept design stage where you don't know the actual product, generic data is most ideal, so REBA stage 2. It can also be useful at REBA stage 4 at technical design, because not all manufacturers have specific EPDs for their products, so you're often using generic data. Consider how many hundreds or thousands of materials and products might go into a whole building. Generic embodied carbon data is still useful, even at technical design and the construction phases too. Now, in terms of standards in this space, one of the most important standards, certainly for European audiences, is EN 15978/2011. Now, this is the British standard version on the cover there, but it's actually a European-wide standard that has been implemented across Europe. Now, this standard is on sustainability of construction works of buildings, and it recognizes that generic data can be used throughout any stage of the project. Concept design, detailed design, construction, use stage, in-use embodied carbon, if you like, and eventual end of life of the building. So generic embodied carbon data is a really important data source. However, it is best when complemented with specific data. Now, specific data, that brings me to environmental product declarations, EPDs. Lee's mentioned EPDs in the presentation. And they're ultimately a short document which summarizes the environmental impact of making a product. And you have an example EPD here. They have quite a standardized way of breaking down the results in these modules, A1 to 3 being cradle to gate, A4, transport from gate to construction site, and A5 is the construction site impacts. And they cover far more than just carbon. So this global warming potential GWP, that's the carbon results. And then you've got all these other indicators here. In fact, there's over 20 environmental and resource use indicators on an EPD. So you can consider more than just carbon if you wish, but most people tend to hone in on the carbon results or the GWP. Now, the EPDs are best applied later in design stages when you know which materials and products have been specified. There are tens of thousands of EPDs out there now around the world. However, not all products will have an EPD, but they are a very useful data source when available. And many of the mainstream products now have an EPD. Now, one thing we've learned by analyzing data for the ICE database, a generic embodied carbon database, is that the variability of the data is really important. So we spend a lot of time analyzing the results of EPDs to get to the generic embodied carbon data for the ICE database. This here shows us the embodied carbon of data in quite a large population data set that we have for one of the materials. And this is probably a classic profile of what we see in the data, this kind of side S kind of curve, if you like, of each of these data points is the embodied carbon of real product in one category of materials. So a consistent category of materials. And you can see here just how high the range of data is. This chart goes almost up to 5 at the high points and down to about 0.5 on the low point. We publish embodied carbon generic data value, this red dot here. However, if you just go and pick a random off-the-shelf EPD and apply it as representative of the whole materials and products and categories without knowing that's the actual product, you might accidentally pick an EPD that's all the way up here or all the way down there. So really, this shows a bit of the value of using generic embodied carbon data when you don't know the actual EPD. If you do know you've got a specific EPD for a product specified, you should use it as a first port of call. But if not, generic embodied carbon data is a good data source too. Now, there are various challenges and limitations. So all databases have challenges and limitations. The key challenges include poor quality environmental product declarations or embodied carbon results. Now, there's many, many good EPDs out there, and there's tens of thousands, which have really helped put together data for the ICE database as generic embodied carbon data. But really, it's the smaller percent of the poor EPDs that cause the issues, because they're not apples for apples comparisons, they're more apples for oranges comparisons, even when claiming adherence to the same standards. So sadly, not every EPD can be fully trusted out there. There are certainly over 90-something% you can rely on the EPD results, but there are certain EPDs that have issues and are not as comparable as they should be. So that's been one of the main challenges we've had to develop generic embodied carbon data. We spend a lot of time going through investigating issues and cleansing out the data from a data set that have issues so we can get to a more representative generic embodied carbon database. We also have access to a lot of data. So we have access to over 100,000 embodied carbon data points in a backend database, which is an awful lot to look and analyze and investigate to get to generic embodied carbon data. Now, there are some limitations of the ICE database. And although we've been working to update it, there are many materials that would also benefit from being updated with newer data. As I said, we have access to over 100,000 carbon data points. So we're continuing to look to see if we can analyze and update materials as we can. Now, in terms of the benefits of the ICE database approach of using generic embodied carbon data, we have, it is really curated data. So we've investigated and analyzed the issues in the EPDs so that you don't have to really. We've removed the problematic ones. So rather than going to pick the first random EPD that you come across and apply it to a project, we've gone through and screened and categorized and investigated the problematic ones to come to a more sensible, typical average for that category of materials. It's also cleansed the representative values where we've done that process to get rid of the data in the background data set that does have issues, which does take some expertise to understand and identify those problematic data points. It also saves time for practitioners where you don't need to deep dive into the underlying LCAs of the EPDs quite so much. You can pick the generic data as representative of that material. And it's also free to access to download from the Circular Ecology website. Now, the ICE database, just in summary, is a free data resource. It's downloadable from the Circular Ecology website. The data is expressed in per kilogram, kilograms of CO2 per kilogram of materials. So you can apply it to your products. You need to overlay some basic calcs on mass, density, etc., and material types to apply it to products. Therefore, it does require a bit of other data and assumptions, but nothing too complicated to apply to actual materials and products and building projects. You're often doing that by estimating the product weight and material composition. It's at this point that I hand back over to Lee.
Thanks, Craig. Yeah, really, really useful information there from Craig. I think one of the things that is probably worthwhile just mentioning, and most people will be aware of this, listen, is if you are looking at doing a life cycle assessment or embodied carbon calculations, as being aware of those life cycle modules that Craig's touched on and that's available in the standards. A is typically your embodied carbon. Moving into B, you have your in-use carbon, which Craig mentioned, which includes things like the energy use in the building through its lifetime, but also replacing materials that are replaced throughout the project's life itself. C then goes into the end of life, so that's looking at things like deconstruction, waste processing, etc. And then D is the end of life of things beyond the system boundary. So if you've got PV, for example, you might be putting energy back into the grid and decarbonising. You might have carbon that's been sequestered through timber construction and things. There's a lot that you can do there. But typically, when you're looking at whole life carbon assessments, the modules are A, B, and C that you're going to be focusing on. This particular webinar is on embodied carbon, which is the upfront emissions that are within the building, as Craig's just explained. And on that note, what I want to announce now is an embodied carbon guide that NBS are going to be launching in cooperation with Circular Ecology. This is going to come out in March, so keep an eye out for that. There'll be some information towards the end of this presentation in terms of how you can access that, where it'll be available from, etc. But ultimately, what we thought would be useful for the industry was some practical methodology for, one, calculating embodied carbon for real world construction products and systems. So the ICE database that Craig's just mentioned is absolutely phenomenal in terms of providing data for raw materials and some manufactured materials as well, but in a kilogram situation. Now, if you're applying those in a typical construction project, if you're going for quantity surveying where you need the quantities, you're typically going to be looking at things in meters squared. If it's building fabric, meters cubed. If it's foundations, that kind of thing. And notably with a BIM model, you will be applying those same units of measurement. So how can you convert those kilogram carbon factors to real worked examples? And that's what the guide's going to do. It's going to talk about how you can do that and how you can apply those values to your BIM objects at the end to actually then use them on real life projects. It'll cover the life cycle stages. We're going to be looking at some worked examples, which I'm going to be talking through now, but those will all be available in the guide. And the different BIM parameters that you need to consider when applying this type of information to it. So the guide itself was authored by Circular Ecology and with input from NBS. It was reviewed by a number of different industry professional persons, which are from industry trade organizations, design practices, consultancies, manufacturers, all which will be acknowledged in the guide itself. But we're quite proud of what we've done in partnership with Circular Ecology, and we're excited to be launching this in the coming weeks. But that said, here is a sneak preview of what it's going to be including. So the key concepts, we talk about how you can source and use generic data sets. Key considerations such as material density. So Craig's just mentioned you need to be factoring things in terms of material density, the mass, and to allow you to convert those kilogram figures into real world examples. And it's all been authored with a geometry-led modeling approach. So we think the guide distinguishes itself by putting that upfront embodied carbon data in the BIM object level. So thinking of it from a BIM perspective, most people will be using things like Revit, ArchiCAD, etc. in terms of their design processes. And that's a great foundation for understanding what's going into that design. Now, if you can factor in the generic carbon early on with that, the chances of achieving your sustainable outcomes and lowering that carbon over the project life are going to be much more high in terms of their success rate. So, how do we get from generic materials to products? Well, the first thing that I think is worth mentioning is how we would consider the products, and particularly from that geometry-led approach. There are different ways that things are modeled, there are different ways that things are procured, and there's certainly different types of declared units that people would want to use to calculate the volumes of those things. So if we took a simple item, so this is a single material, something like mineral wool insulation, as we've got for example here. That is a single layer material. To calculate the carbon of that, it's quite a straightforward process, but there are things that you need to watch out for. We will go through worked examples in a moment, so I'm not going to cover that right now. This is just an overview of the approach. There's then layered assemblies, which could be something as we've got there, which is an insulated cavity wall. That particular build-up that's shown there is very typical of any residential part house build-up at the moment. That is basically a sandwich of those simple items. So we need to understand the simple items to be able to calculate that. There are then others. So composite assemblies, if you are specifying reinforced concrete, for example, whether that's in a raft or a pad, or if it's a pile foundation, as we've got as the example there, volumes play a really important part in this. Now, with a BIM model in particular, the geometry would be modeled for the cylinder of the pile foundation, but it wouldn't contain the geometry for the rebar that goes in that. So being able to understand out of that composition how much is concrete and how much is actually steel is key in understanding these things. There's then complex items. So these are slightly different than simple items in that you need to apply a manufacturer uplift for this. They are off-the-shelf products that you would be able to buy from a merchant, for example, like you can for mineral wool insulation. You could go and buy a radiator just as easily from a builder's merchant or direct from the manufacturer in some cases. However, the radiator itself would use raw material data in terms of things like steel or brass from the ICE database, but then that would have to have a manufacturing uplift applied to it. So we're going to be talking about how you can apply that to give you a more accurate figure in terms of a generic manufactured product that's been assembled in a factory, for example. So to begin with, we're going to start with the simple items, and we're going to focus on the A1 to A3 carbon in this particular case. We will get into transport to site, which is A4, and we will cover construction, which is A5 later on. But for all of the products themselves, we are focusing on cradle to gate at the minute. So we've got this example, which is mineral wool insulation. We've got the Uniclass code there, which you can see. We've got the ICE material reference, and then the ICE embodied carbon value, which is 1.25 kilos CO2 per kilogram. We know the thickness of this, so if we were specifying 100 mil thick mineral wool insulation, we'd also then want to know how many meters squared we're going into the building. So in the BIM model, the different faces of the building envelope would be measured in meters squared, so we need that. But we don't know the density at this point because it's provided on a carbon figure per kilogram basis. So we need to do a little bit of maths and we need to add some additional figures in to give us that meter squared rate for the mineral wool. So the calculation for this is thickness times density, which will give you that mass per unit area. So we need to understand the density. Now, there's a lot of places where you can get density information from. NBS source has multiple different manufacturers' products in there, which you could look at averages from there, or there are generic data sets. So this particular one that's in this example has come from the SIBSI Table A, which is 24 kilograms per meter cubed of mineral wool insulation, specifically a BAT in this case. Now, insulation, notably mineral wool, the densities can vary quite drastically depending on the application. One, is it going in a wall? Is it going in a loft? Is it a rain screen slab? Is it made of stone wool? Is it made of glass wool? The density does vary a hell of a lot. So it's not good enough to just use one set density. You need to be factoring in the application as well with this. So we've got this assumed density here from the SIBSI guide, and it's 24 kilograms per meter cubed. So at 0.1 of a meter thickness, so 100 millimeters, we know that that's 2.4 kilograms per meter squared for the mass. So from that, we can use the ICE data. We can take that mass that we've calculated and we can multiply that by the embodied carbon factor that the ICE database provides us to give us the value of 3 kilograms of CO2 per meter squared. That is the embodied carbon figure for your specific mineral wool insulation. So pretty straightforward GCSE maths. There's just some unknowns that you've got to factor in. So always think about that. Then moving on to layered assemblies. For this example, we've got that masonry cavity wall. It's 102 mil brick with 150 mil mineral wool insulation, 100 mil concrete block, and then a plaster finish on the internal face. We've got the Uniclass code there again. Classification, just mentioning this, quite important. I think if you want to keep reusing these data sets that you may build up, having them classified and structured is really, really key in terms of applying them to your BIM objects. Particularly if you're looking at ISO 19650 and the BIM framework there. Uniclass is referenced as the classification system for applying to these things. So if you are wanting to apply values to your project, it's a good starting point, and then you can build up these data sets that can be reused time and time again. We've got the title. The ICE material reference varies depending on what the material is. So is it brick, insulation, block, etc. And then we know the overall thickness, and we need to know that per meter squared. So instead of having to calculate on your project every layer individually, you could actually build these data sets up, and then you could just apply it per meter squared for the system as a whole. So in this particular case, we would have followed that previous simple item process where we would have been finding the density for the insulation. We would have known the density potentially for brick because the ICE database does contain some material densities that you can use. And then it's just a case of adding those different layers together. So if we look at layer one, we've got a meter squared of brick. We've got the ICE material reference for brick, which is available from the ICE database. The ICE embodied carbon figure for kilograms of brick wall. The thickness, which is 102.5, and then the density, which is just short of 1,500 there. The mass per unit area from that, which we can then calculate from the density and the thickness, is calculated here. And then all we've got to do is take that mass per unit area, again, like we did previously, multiply it by the carbon value to give us the total embodied carbon per meter squared. We then do that for each layer individually, and then it's just a case of adding those up. So in this particular case, we've added those 4 layers up, and it comes in with 51.66 kilograms a meter squared for that particular wall makeup. Having data sets for assemblies like this would be really, really valuable and time saving for something that would otherwise be very time consuming. So for that reason, we thought this would be useful to explain. Then with the composite assemblies, we know that this particular pile foundation is made of a certain grade of concrete, and we know that it has steel rebar contained within it. But to determine the carbon value, we need to know the percentages of each. So what you can see here is material 1. We've got an RC4050 mix concrete, and there's per volume 95.5% of that pile is concrete. We've got the ice material reference for that specific mix of concrete, and then we've got the ice embodied carbon value, A1 to A3 there per meter cubed. Now, just worth noting, for some items, notably concrete, the ice database does include meter cube values. So in that case, we don't specifically need to calculate what that would be per meter cubed. But then for some things, it is still just on the kilogram basis. So if we look at the material 2, which is a steel rebar, 4.5% by volume is steel rebar. We've got the ice reference, but then the embodied carbon value is per kilogram. So really, really important that when you are calculating, you take note of the declared unit. Is it meter cubed? Is it meter squared? Is it per kilogram? Is it per unit, etc.? And likewise with EPDs, if the manufacturer EPDs that you're using, you may compare one for one. And one manufacturer, say it was a window, for example, may have had an EPD created per window unit. The next one might have done it per meter squared of window. So the carbon values won't always be directly comparable. You will need to do some calculations in terms of normalizing the declared unit values there. Now, NBS source does do that. If we have enough EPDs that are put into the system and the manufacturers have entered the data, we are actually normalizing this so you can compare those apples for apples in terms of an EPD. But going to generic, this is where it will require some little bits of maths from yourselves. So in this, we know by volume where it is for concrete. We've got to do the calculation then for the steelwork itself. So material density is 7,850 per meter cubed. The embodied carbon factor is 0.73 per kilogram. So if we multiply that density by the carbon weight, it gives us 5730.5 kilograms of CO2 per meter cubed. From that point, then we've filled in those missing gaps and we can do the calculation. So for material 1, which is the concrete, we know that it's 381.52 kilograms per meter cubed and the percentage is 95.5%. So it's 95.5% of that. Material 2, the steel rebar, we know the carbon value now per meter cube because we just did that calculation and it's that times 4.5%. We add those two together and it gives us that total. So for this specific concrete pile, it's 622 kilograms per meter squared. Actually, sorry, per meter cubed for the concrete. Then moving on, complex items. So the ICE database does contain some materials that have included things like the manufacturer uplift. So there is data in there for sanitary ceramics, for example. So what would be the carbon value for a wash basin or a WC pan? But for a lot of manufactured goods, they are complex fabricated assemblies. A radiator, something simple that everybody's familiar with, has a lot of different manufacturing processes that will go in with there. There is punching, pressing, folding, welding, brazing, assembly, that there's a lot that goes in. So that's where this manufacturer uplift needs to go in. Now, to do this, it is possible to use generic manufacturing uplift figures, which are available if you do a bit of a Google search. But possibly one of the most robust ways that you could do this would be to use the CIBSE TM65 embodied carbon methodology. Now, this requires to actually achieve an A1, an A2, and A3 breakdown figure, inputting some manufacturing information. Now, obviously, for a generic product, you're not necessarily going to know what that is. But if you can estimate this, there's a whole host of information that's available online. You could quite easily find some figures that would suit what it is that you're going to do. So in this particular case, we know that we have a meter squared radiator, so it's 0.1 meter cubed, it's 100 mil thick. The product service life typically is going to be 15 years. We would know that from experience of how often heating appliances have to be replaced. The product weight, we've taken this from an average of different radiators from different manufacturers, 65 kilos. And then the material percentage, so what goes into this? Steel, is it general or galvanized? Powder coating, there might be brass in there. All of this data that we've used in this particular case is what we would find in a typical makeup of a radiator. And coincidentally, the ICE database is the data source that CIBSE TM65 uses. So when you're building in generic materials, to calculate that whole assembly, it's actually the ICE data. So when you're coming out with the end result, it's giving you a like-for-like comparison again to the other things that you've just been doing. We've set the location of the factory central in the UK, annual factory energy at 200,000 kilowatts an hour, and then the annual tonnage of product that's made is at 500. We can input that into the TM65 calculation tool. Now, for CIBSE members, I think the TM65 is freely available. For non-members, it's relatively cheap. You're talking around £100, I think. I can't quote the exact figure, but if you visit the CIBSE website, it's available there as a download. And this would allow you, as a manufacturer, to actually calculate your embodied carbon for your product, as well as some of the other figures. Or if you weren't a manufacturer, you could use this for estimated figures for generic uplift. So what we've got there is we've inputted all that data. The TM65 methodology and the tool itself has actually done the calculations using that material data from the ICE database, and it's given us the figures, which you can see. A1 material extraction, A2 transport, and A3 manufacturing are broke down, notably because we've done a mid-level report. TM65 does offer a basic report, but it includes A1 to A5 as a whole, so you can't necessarily break that down without doing the mid-level report. It's then just a case of adding those together once we've got them. So for this particular radiator, generic, 235 kilograms per meter squared. Now, in the BIM environment, a model of a radiator will typically be parametric, particularly if manufacturers offer these things in different sizes. Some might do bespoke sizes, depending on what the volume of your room is and the heating capacity that you need. So meter squared is a great way of applying this. You can then scale that up and down dependent on what you need. But checking that out, we've looked at this across manufacturer EPDs, and the figure checks out. It's similar, so it's pretty much a good base point to actually start with. So once we've calculated the actual manufacturing emissions, so A1 to A3, so that cradle to gate bit, we need to factor in transport to site. Transportation to site is typically done by the mass of material that you're transporting, multiplied by the distance, and then the emission factor for the transport method that you're using. The embodied carbon guide that we're going to be launching will include examples on how to do this, and Circular Ecology have written a great piece in terms of how you can go about doing this and how they would do that in their own LCAs. Factoring in emission factors from places like the Department for Energy, Net Zero, the greenhouse gas conversion factors that give there, things like cargo ships, heavy good vehicles, etc., all can be referenced, and then we can actually use that to work out what the well to wheel is. So to calculate that distance, we need to factor in tank to wheel. So that's the fuel being taken from the tank to the wheel. If it's a ship, obviously it's going to be to the rudder and the propeller, but it's obviously road transport. It's going to be tank to wheel, and then well to tank as well, which is that oil or fuel being taken out from the well and then produced and put into the tank itself. So we need to combine those two things together. Very, very important that we factor in the well to wheel factor there and not just take in tank to wheel or well to wheel. To do this, then we can work out what the emissions are based on that. So if we know that the tank to wheel is 0.097, we know that the well to tank is 0.02. It's a case of just adding those together to give us the 0.12 overall figure, which is the kilograms of CO2 per ton kilometre. An example of how we would use that in a calculation then would be if we were transporting a specific material or a product from the manufacturer to the construction site. It might go through two methods of transportation. There might be part of the journey done by HGV, part of it done by cargo ship. We'd have the selected descends factor. We'd have the transport distance, so how much of each is done in terms of kilometres per road or by sea. The transported mass, which in this particular case remains constant because it's the same load that we're transporting across both, and then the ton kilometres. So we can apply those factors using the tank to wheel factor, the well to tank factor, and we can calculate those to give us the individual figures for each. So total well to wheel carbon factor in kilograms CO2 per ton kilometre, 0.1211 for the HTV and 0.0162 for the cargo ship. The transport emissions then, we've got these from Department for Environment, Security and Net Zero. That's actually included there. And then it's just a case of adding those two together, which would give us that total A4 transportation factor, which we can factor in. There are default waste rates, transportation rates that can be used. Might be worthwhile looking at those. They can provide an easy calculation, but if you do want to factor this in specifically, that is the methodology. Probably a very quick waffled overview of how that's done, but the guide itself will include the full details. So keep an eye out for it and have a go at doing this. Then the final stage for the upfront embodied carbon is A5, which is the construction and installation. Now, A5 is split into 4 submodules. A5.1 is the energy use from machinery, etc., tools during the installation. Any auxiliary materials packaging is 5.2, and then 5.3 is the waste. So this is how much material gets delivered to site and ultimately gets chucked in the bin or recycled at the end. And then 5.4, which is optional, accounts for temporary site facilities, handling equipment, that kind of thing. So if you've had a porta cabin, for example, put on the site, the energy associated to that, or if you've had a crane put in, the energy use associated with that. But for this particular assessment, when we're looking at it from a product level and the BIM objects, A5.3 is the main area of focus that you want to be looking at. So this is the construction waste. For this, I think overall anyway, construction waste could be anywhere between 50 to 80% of the total A5 count. So it's the biggest factor that you need to be thinking of. And from a product perspective, it's arguably the most important there. Waste rates are available from different places. So RICS have a default one, which is in their whole life carbon assessment for the built environment. A lot of whole life carbon assessments now are using the RICS guide, and it's something that is referenced quite heavily when we produced our guide on calculating these embodied carbon factors and applying them to the BIM objects. A lot of the feedback that we were getting was that people are using this RICS whole life carbon assessment methodology now. So something to worth look at if you've not taken a look at it yet, but that's there. There are also lots of different places where you can actually get these from. So BRE have it for their product category rules for EPDs and construction products. Product Association, so the Mineral Products Association was one that contributed to the guide. They will have different waste rates that they will have available, but if you can take one, pick it, use it, you're going to have consistency throughout. There are many others, but the webinar isn't long enough, unfortunately, to sit and actually list all of those that are available. So from that, what you would do is you would take that waste rate, which would typically be a percentage of your A1 to A3 emissions. So what we calculated earlier for the particular products and systems themselves would be multiplied by the waste rate percentage. So if the waste rate was 15% and your A1 to A3 was 100 kilograms, it would be 15 kilograms of emissions for A5. Pretty straightforward. Again, the guide will cover this in detail, so keep an eye out for that. So once we've done all those calculations, how do we apply them to BIM objects? Well, pretty much most of the BIM software that you'd be familiar with using will have dedicated property sets. Revit itself, which is by far probably the most adopted software now in the industry, in the UK in particular anyway, has had green building properties available within its BIM objects for as long as I can remember. Applying data sets to that is a great way to then be able to use these in schedules and outputs moving forward. ArchiCAD and Vectorworks in their 2026 iterations also introduced similar schemas. ArchiCAD has the property group for building materials, which is focusing on environmental properties itself. And Vectorworks has now got a sustainability dashboard. So if you are using something outside of Revit, take a look at those and you should be able to transpose. But importantly, it's that embodied carbon figure that we're looking for. At minimum, Your objects then should include the name and the category, goes without saying, just so they can be classified and you can identify them from the schedules. You need those different material layers and thicknesses and the types that we're looking at through the worked examples. And then thicknesses and densities. I can't express enough how important thickness and density is if you are looking at doing those calculations. What you don't want to be doing is taking something and then having a carbon value applied to it, but based on your thickness or a different density that you're doing, the value doesn't apply, or you can't actually perform the calculation. So make sure that that's included. The unit mass then, or the mass rate, so kilograms per unit in that particular case, is something that should be included, and then the embodied carbon factor. So in this particular example that we've been looking at throughout this webinar has been the data from the ICE database. Where you've got your carbon value from, what it is, cite that, and you'll be good to go. Make sure that you've got the declared unit right for what you're doing. So you don't want to be specifying per meter squared if your value is actually per kilogram. So again, 100% need to double check that to get sure that it's all working correctly. Then you've got your figures. Once you've done the calculation, we want to make sure that we've got A1 to A3, and it's always worth separating these out, not doing them as a whole. You can summarize them if you want in the end, but I would recommend including A1 to A3 as a separate line, A4 as a separate line, and then A5 as a separate line. That way, you're future-proofing. If you need to break down or pull out specifics, you can look at different areas of where you can actually make any improvements there or report on this on an individual basis. You want the declared unit for your calculated embodied carbon figure. So looking at this, if we went for the embodied carbon factor from ICE and the declared unit would be kilograms, our calculated one in this particular case, if it was for mineral wool insulation, like the first example, would be per meter squared. So you need to make sure that those are factored in. Also worth having a notes section where you can add any exclusions or assumptions. So if you were doing that masonry wall, you might not have done the calculation for wall ties or lintels, which we didn't do in that example. So noting what is and is not included helps people to reference that later down the line. And then any additional notes that you would like to add. And then finally, once we've actually pulled all those together, the data can be added in. Now, it is worth noting that some of those properties, particular things like classification or the BIM object name, will sit within other data sets. Some will be the hard-coded properties that are within the BIM objects themselves. Some might sit within COBie. Don't replicate them. You can reference them. You can do an equals to and link the parameters together, or if not, just rely on the ones that exist and only add in the sustainability properties that are additional to the existing data sets. In Revit, we've got some screenshots here. Apologies for the visibility on this, but it is a screenshot taken direct from the screen. You can go into the parameter properties and you'll find green building properties in the drop down on where to group the properties under. Give them the name, set whether it's type or instance, whether you want to report on that or not. And you can apply those figures, which in the end would give you a sequence like this, which we've got A1 to A3 carbon source, the factor, the density, the declared unit per kilogram, and then we've got those A1 through to A5 figures there that you can see, and any exclusions that have been included. That then, for this particular wash basin example that we've got, if we then put 300 of those into the BIM model, if it was something like a hospital that we were designing, very, very quickly could output the summary schedule and the total carbon values for those products in one go. So yeah, I understand probably a bit of a brain dump there and a lot that's been going on. In conclusion, just to summarize what we've just been talking through, the industry needs applied generic values alongside EPD data. Early stage in particular, and whilst there are gaps in different categories for EPDs, you're going to need generic to actually plug those holes at the later stages. The ICE database itself provides a reliable baseline for material values, so highly recommend downloading that and taking a look. Early stage design, generic values are very, very good for comparisons and option appraisal. So if you want to look at those different options with your client, being able to use these values and say, well, look, if we use this specific material or this specific strength, we can reduce the carbon by X. Give them some options. You then are going to be covered in terms of starting that sustainable outcome journey at the earliest possible stage. Application of data within BIM, it can automate lots of reporting. There will be a caveat in terms of not everything's always modelled. An architectural model might not have the foundations model, for example, so you will need to combine things like the structural model, the architectural model, the MEP model, for example, if you wanted to do that full calculation. But in terms of early stage, particularly if you're looking at building fabric, it's a real good place to actually start to do this. And then the limitations, generic data versus EPDs. Start with generic, transition to EPDs. If you use a manufacturer-specific EPD at too early a stage, and that might not necessarily be the product that you're going to be using later down the line, it could have some quite dire consequences in terms of the count. It could be plus or minus. It might be close if luck happens, but using generic will always give you that good benchmark. And then from that, as you specify manufacturer products, you can always show how you're improving using specific manufacturers and the products that they're offering in terms of low carbon options. And last but not least, transparency and consistency are critical. Use the same data sets. Make sure that they're robust. Keep using them. Don't be doing different calculations each time, which could give you different results for the same thing. And explain what isn't included, how things were calculated from a methodology point of view. Next steps, then, the guide itself from NBS and Circular Ecology will be launched in March. It will cover all of the points in a lot more detail than I've just very quickly ran through in this webinar. Highly recommend downloading it, taking a look, use it. It will have some supporting BIM object examples. So the worked examples that we've just talked through, there will be some downloads that you can use and reference. You'll be able to use those in your own project or use them as a basis to replicate the different materials and products and systems. Anybody that's joined the call today will receive the email link, but generally it will be available to download for free at the nbs.com. Yeah, use those examples, download it, share the feedback. We'd love to hear any comments or anything that are on the back of that after you've been able to take a look at it. And yeah, good luck with your carbon reporting and helping to decarbonize the industry. I'd like to say thanks to Craig for joining me today and providing the valuable insights into the guide from Circular Ecology's perspective. And also a final mention to thank our sponsor, Johnson's Trade, for allowing the webinar to happen today. If you'd like to know any more information about NBS or the guide itself or what you've heard today, feel free to add a question in the comments now just before the webinar finishes, or if it's too late, drop us a note at info@thenbs.com. I've been Lee Jones. Thank you very much and have a pleasant rest of your day.